In 3.1 and 3.2, we got a lot of practice with using the limit definition of the derivative. Okay? That is how the derivative is defined. Okay? Unfortunately, the reality is 20 years from now, when somebody asks you about calculus, many of you will just say, oh, you bring down the power and then subtract 1 from it. And that's what you'll take away from calculus. That's too bad. But that's the reality of it. If you're not using it, that happens. Okay? But that is not calculus. Okay? Calculus was this idea of bringing the secant lines, the points of the secant lines closer and closer to one another to get the tangent line. That closer and closer involves a limit. So you cannot talk about a derivative without a limit. Okay? But we don't like to reinvent the wheel every single time. So what we'd like to do is come up with a series of shortcut rules for taking derivatives. Okay? I'll prove some of these. Today I may not prove too many of them just because we're trying to make up for lost time. Okay? But we're going to get some shortcut rules for taking derivatives. Okay? All right. So the first rule is that the derivative of a constant function is 0. Now I want you to think about that one for just a second. If I asked you to graph this function right here, here's the graph of f of x equals 3. What does the derivative do? It tells you the slope of the tangent line at any point on the curve. If I pick this point on the curve right here when x is negative 4 and I drew a little tangent line there, what is the slope of that tangent line? 0. If I pick this point right here at x equals 2 and drew a little tangent line, what is the slope of that tangent line? 0. So without doing any work, we should see that the derivative of f should be 0 everywhere. Okay? Don't forget this sort of intuitive way of looking at a derivative. Okay? But let's actually prove that using the limit definition. Okay? So here's the proof. Well, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. But this says take the function f. What is f in this case? Well, for the one below, it's just 3, right? But for up here, it's c, an arbitrary constant. I chose 3 in my example below. But it's just an arbitrary constant, right? So for example, if this were f of x equals 3, and I plug in 20 for x, what does it output? 3. Or if I plug in 50 for x, it outputs a 3. So if I input x plus h into this constant function, it's going to output c, right? And if I input an x into this function, it again outputs c all over h, okay? Which is equal to the limit as h approaches 0 of 0 over h, which is equal to the limit as h approaches 0. H isn't 0. A number 0 divided by any number is 0. What is the limit of a constant? It is just the constant. So, using the limit definition, we've proven that the derivative of a constant function is 0. Okay? All right. For the next one, we say that the derivative of the identity function is 1. Okay? Let's look at the graph and let's see if that makes sense. Here's my identity function, right? It's the graph that, you input a -4, it spits out a -4. You input 20, it spits out 20. Okay, it's called the identity function, f of x equals x. Okay? Anywhere along here, if I drew a tangent line, what is the slope of that tangent line? What's the slope of that tangent line? It's 1, right? Everyone okay with that? The slope of that line right there is 1, so the slope at any point on that line should be 1. Okay? First of all, the derivative is a tool that's supposed to linearize things, right? So when you take the derivative of a linear function, it's not very interesting, right? Okay. So the derivative of the identity function is just 1. Okay? Oops. Let's prove that. So here we talked our way through it. We looked at the graph. We talked our way through it. But we can use the limit definition to arrive at the same conclusion. Okay? Boy, he sure writes that definition a lot. Well, I want to make sure I don't forget it. You should too. You get a point if you do. Okay. What is f of x plus h? Well, this is the identity function x. So when I replace x with x plus h, I've just got x plus h, right? Minus x all over h, which is equal to the limit as h approaches 0 of h over h, which is equal to the limit as h approaches 0 of 1. And the limit of a constant is just itself. In the interest of time, I'm going to skip the x squared function. Let's just say it. I'm going to skip it. But let's just say that f prime of x we would find to be 2x. Okay? You should do the work to fill that in. Okay? In fact, I'd make a nice quiz question next time. I'll let you do the work. Okay?
Can you back up just one second?
Yeah, of course. To number 3?
Yeah. Okay.
Yeah. Are there any questions on that? Yeah. Let's look at the graph of x squared. The graph of x squared looks like this. Oops, that's not quite right. I can't quite see these lines on here, folks. 2 gives a 4. Minus 1 gives 1. Minus 2 gives 4. 0 gives 0. Here's the graph of x squared. Okay. Its derivative, you would find when you do the limit procedure, is 2x. Okay. And you guys already told me that answer. Remember, we did that in section 3. Well, yeah, section 3.2. We did this, or maybe it was 3.1. Yeah, it was 3.1. We started with the parabola, okay, and we said, hey, this was the very first one we did. We said, hey, what's the slope of this line? We said m was equal to 1 at the order pair 1, 1, right? And at the order pair 2, 4, the slope of this line was equal to, oops, I'm sorry, that was a lie here. The slope was equal to 2, we found. And this slope we found was equal to 4. Okay. We didn't do it for this point over here, but what would be the slope of this line right here? -2. Right? Notice that whenever green, well, I've got different colors. Whenever f is decreasing, its derivative is what? Negative. Okay. So be careful. Don't say it's decreasing so it's negative, or it's increasing so it's positive. Ignore the word, or try to avoid the word it. Right? When f is increasing, f's derivative is positive. Okay? Okay. Let's skip this. Well, let me give you the answer. So f prime of x we would find to be 3x squared, and you can do the work to show that. Okay? So I'm skipping some of the work on this, just trying to make up for lost time. All right, so here would be the graph of x cubed. This is a really important one, I think, to look at. So if we plug in 2, we get out 8. And that's as far as we can go. And if we plug in -1, we get out -1. Plug in -2, we get out -8. So here's the graph of f of x. Okay. And we plug in 1, we get out 3. We plug in 2, we get out 12. And minus 1, minus 2. Okay. Folks, some of the points on here, for example, this is the order pair 2, comma 12, and this is the order pair minus 2, comma 12. Okay. How am I getting those ordered pairs? I'm using what we said the derivative was on the previous page. So we've got f prime of x, which we said was 3x squared. So if I plug in a 2, I get 2 squared is 4 times 3 is 12. Everyone okay with how I found those ordered pairs? Please, 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 somebody stop me and say you did too fast on that. Yeah, Will. I did too fast on that. Thank you. Okay. Here is the ordered pair. Here's the ordered pair 2, comma 8. Does everyone see how I got that ordered pair on my cube function? I plug a 2 in for x, and it outputs an 8. Okay? I said, although we didn't prove, that the derivative of this function is 3x squared. So if I want to find the slope of the tangent line right here, if I want to find the slope of that line right there, I'm going to plug 2 into the derivative, because that's the x coordinate. Okay? So f prime of 2 would be 3 times 2 squared, which is 3 times 4, which is 12. So the slope of the line right here is 12, and that's reflected in the fact that the derivative outputs a value of 12 there. Thanks for slowing me down. Questions on that? Okay. There's something really neat to observe here. This function is increasing over its entire domain. So its derivative is always either positive or 0. There's one place where I have a horizontal tangent line, that's right here. That's precisely at this ordered pair right here, 0, 0. Right? But notice that everywhere else, when I draw a tangent line, what is the slope on those tangent lines? I want everyone to say this. Everywhere along here, as I put tangent lines, what are the slopes of them? They're all positive. What are the y values of the derivative of this function? They're always positive. When I look at the graph of this derivative, I see that this function should be always increasing. You want to talk about that? If the derivative is always positive, then the function must always be increasing. Okay. How are we doing? We're okay. Let's look at something called Pascal's triangle. Okay? Pascal's triangle is a way of coming up with certain coefficients for lots of useful things in math. Okay? The first row is when n is equal to 0, and you just put a 1 there. Okay? The second row is when n equals 1, and you put 2 1s like this. At this point, I don't think you should see the pattern, unless you think it's always going to be 1s. Okay? For the second row, I go 1, 2, 1. For the third row, I go 1, 3, 3, 1. For the fourth row, I go 1, 4, 6, 4, 1. Now I think we might be able to discover the pattern. Go ahead, Will. No? Who thinks they see it?
I believe that you.
When you add them, you start at the top, you have, because 1's 0, and then you do 1 and 1, and then in the center it's 2. And if you go from the left of it to 1 plus 2, and you go down the triangle is 3, and you go to the other side, it's the same thing. And
1 plus 2 gives me 3 there.
yeah, and then you keep doing it down, and then in the center, the same thing happens, 3 plus 3 plus 6. Unless I'm completely wrong.
Nope. You're right on. Okay, does everyone see how we get the next row of Pascal's triangle? So we take the two numbers immediately above it, add them together, that gives us the entry below it. Okay? With the exception of having all 1s along the two diagonals. Okay? So help me out. What would be the fifth row here?
1, 5, 10, 10, 5.
1. Why is this one 5?
4 plus
So add 1 plus 4. Okay, anyone not seeing it? This would be what? 10. This would be 10. This would be 5. This would be 1. Okay. I don't remember what this. Oh, yeah, I don't know why I have this third row. It confuses me. Anyway, if I take a plus b to the 0th power, what does that give me? What's anything to the 0th power? 1. If I take, I guess this is what I'm going to do, a plus b to the 1st power, that gives me just a plus b, right? I'm going to write that as 1a plus 1b. Okay? If I take a plus b to the 2nd power, over here we have this 1. If I take a plus b to the 2nd power and I FOIL that out, what do I get? I get 1a squared plus 2ab plus 1b squared. Anyone see what's going on here? Who wants to say what's going on here? Do one more? Let's do one more. If I do a plus b and I cube it out, eventually I would end up with 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. What's that? Who said that? Desiree, what do you see in? What's like the triangle? The coefficients, let's take the, well, all these have circles on them. The coefficients come from the corresponding row of Pascal's triangle. That's really handy. Okay? That means that if I asked you to take a plus b to the 5th power, you could do that really quickly. It would be 1a to the 5th plus 5a to the 4th b. What's happening to the powers? You start with a to the 5th, it decreases by 1, while the powers of b increase by 1 each time, right? So this gives me then plus 10a cubed b squared plus 10a squared b cubed. I'm running out of room. Plus 5ab to the 4th plus 1b to the 5th. And I just raised that to the 5th power with no work at all. Okay? All right. So I would like to do this one, the proof of x to the 4th derivative. Okay? So I've skipped a number of them. You can follow the work from previous examples or the work from this example to fill in the work for the ones I've skipped. Okay? So what is f prime of x? It is the limit as x approaches, or excuse me, as h approaches 0 of f of x plus h minus f of x all over h. So that's going to be the limit as h approaches 0 of x plus h raised to the 4th power minus f of x, or sorry, minus x to the 4th power all over h. I'm going to have to FOIL this out. Well, normally that would be a pretty daunting task, but we now have Pascal's triangle. So we get x to the 4th plus 4x to the 3rd h plus, I've forgotten, 6, yeah, plus 6x squared h squared plus 4xh cubed plus h to the 4th. That's all of this raised to the 4th power minus x to the 4th. That's that last part. Let me put parentheses around that so you see that. That's that. Okay. All divided by h. Okay? I'll let you do the rest of the work. There's some steps to be filled in here. Notice that what happens to the non-h terms? They cancel out. Then I factor out an h. Then I can do direct substitution. But what I'll be left with is 4x cubed. If you don't see that, that's okay. Just do the work. You'll get there. Because eventually I'll be able to apply direct substitution, and the only term that no longer has an h in it would be this one, because that h got factored out and then canceled. But all of these other terms, this one, and this one, would still have h's in them, so they'd all go to 0 when I let h be 0. If you don't see that, it's just a matter you got to work it out. So just keep working with this. You'll get there. You've got the tools to do it. What's that?
If you do the 4 0 to the cube, it's gonna be 0 for the whole answer.
Okay, so let's finish it out real quick. So this gives me the limit as h approaches 0 of 4x cubed h plus 6h squared plus 4x h cubed plus h to the fourth. The x to the fourth term's canceled. I can now factor out an h. So I've got the limit as h approaches 0 of 4x cubed plus 6x squared h plus 4x h squared plus h cubed. But this can now be evaluated through direct substitution. So this gives me 4x cubed plus 6x squared times 0 plus 4x times 0 squared plus 0 cubed. So all of those other terms die out. Sorry, it's a little morbid. All those other terms go to a better place. Okay? Send them to the farm. All right. So let's give the power rule then. Okay? So maybe you've noticed this, but if we take the derivative of x to the n, if you look at the pattern that we've seen as we've gone through these, it's just n times x to the n minus 1. Okay? I'm going to skip the proof, but it uses Pascal's triangle basically. You do it generally and you show that you can always do the procedure that you just saw. Foil it out, the first and last terms cancel, factor out an h, all but the second term then vanishes, and you're left with this. Okay? So, let's practice a few of these. Here I've got the function f of x equals x to the sixth. If I ask you to find the derivative from here on out, and I don't say you must use the limit definition, okay, then you can just say that f prime of x is equal to what? Well, the power rule says bring down the exponent. Everyone say that with me. The power rule says bring down the exponent. Okay, what was the exponent?
6.
So there's a 6. Okay, and then take x to the, subtract 1 from the exponent. What do I get? Okay. Unfortunately, 20 years from now, that's all you'll remember about calculus. Unless you're actually doing math in your job. Okay. So what is dy dt? Help me out, folks. What's dy dt equal to? It would be 4t cubed. Okay. What is y prime, folks? For b?
154 x to 130.
Okay. Okay, let's skip d because I realized I didn't give this to you yet. Okay. Later on, I'm going to do a proof of what's called the generalized power rule, which means that this n does not have to be a nice natural number. It can be for any number, any real number, 0.5 or pi or something like that. You can still apply this rule. Okay. I'm also going to just skip the proving the constant multiple rule. But what do we remember? We remember constants come out of derivatives. Now be careful. What was the derivative of a constant? 0. This is the constant multiple rule. Let's be a little careful with that. Oh my goodness. All right. So I'd like to look at number 16 here, and we'll do a couple of these real quick. So number A says to find the derivative of this function here. Okay. F prime of x would be equal to minus 24x to the 7th plus 14x to the 6th plus 4. If you like, let's maybe write a minus 0 here so you can see what happened to the constant term. Okay? So folks, I know some of you have seen this story before, so this should be feeling very straightforward. But some of you, this is your first pass through, which is wonderful. Okay? Your first time seeing this. What happened here? Well, I applied the power rule and the constant multiple rule simultaneously. The negative 3 just came along for the ride. I brought down the power of 8. 8 times negative 3 gives me negative 24. Subtract 1 from the exponent. Any questions on that? Okay. All right. I'm afraid I have to leave you there. We're going to pick up with this next time, okay, and just keep going.